Welcome to Ultimate Sleep Doctor. Tonight, we'll turn our attention to the ancient rhythms of our world. The earth beneath our feet isn't still. It's a living, breathing sphere, constantly reshaping itself across vast stretches of time. Gigantic plates like colossal, silent dancers slowly move, driven by forces deep within. Continents have drifted across oceans, mountains have risen from the seabed, and new lands have formed where old ones vanished. This gentle movement, known as plate tectonics, explains so much of what we see around us. Consider this: everything you know, every landscape, began with this slow, profound transformation. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift, allow yourself to settle. Let's begin. The Earth, our wonderful home, isn't a static, solid thing. It's a restless giant, constantly shifting and changing over vast stretches of time. For centuries, scientists simply assumed the continents had always been where they were, fixed in place like giant, immovable islands. But then, in the early 1900s, a German meteorologist named Alfred Wegener came along with a truly revolutionary, though initially quite unsettling, idea. Wegener proposed that the continents hadn't always been fixed. He suggested they had once been joined together as one massive landmass, which he called Pangaea, Greek for all land. Wegener built his theory, known as continental drift, on a remarkable collection of evidence. One of the most compelling pieces was the jigsaw puzzle fit between the coastlines of South America and Africa. It wasn't a perfect match, of course, but the shapes of the continents seemed to fit together remarkably well, like pieces of a giant, ancient puzzle. He noticed similar geological features. Mountain ranges, for example, appeared on opposite sides of the Atlantic Ocean, suggesting they were once connected. Furthermore, Wegener found compelling evidence from fossils. He discovered identical fossils of the reptile Mesosaurus in South America and Africa, but Mesosaurus was a freshwater creature. It's impossible for a freshwater reptile to have lived in the saltwater oceans that separated those continents. This indicated that the continents were once joined, allowing Mesosaurus to inhabit a single, vast body of water. Similarly, he found the fossil of the fern Glossopteris in South America, Africa, India, and Australia. Another creature adapted to colder climates, suggesting a single, large landmass surrounded by a giant southern ocean. He also examined ancient glacial deposits. Wegener found large, flat areas covered in glacial rocks in South America, Africa, India, and Australia, areas that today are much warmer. These deposits indicated that these continents had once been located closer to the South Pole, where glaciers could have formed. The presence of similar glacial features in these widely separated continents strengthened his argument. Wegener attempted to explain the mechanism driving this movement. He proposed that continents plowed through the oceanic crust, much like a ship cuts through water. However, he couldn't provide a plausible force to cause this movement. He suggested the continents were dragged by tidal forces or by the Earth's rotation, but neither of these explanations held up to scientific scrutiny. Despite the mounting evidence, Wegener's ideas were met with considerable skepticism and resistance from the scientific community. Many geologists couldn't accept the idea that continents could move through solid rock. They believed the Earth was a stable, unchanging entity. The lack of a convincing driving force for continental movement was a major obstacle. His theory was largely dismissed, and Wegener's work remained largely ignored for nearly 2 decades. It wasn't until the 1960s, with the development of new seafloor mapping techniques and the discovery of magnetic stripes on the ocean floor, that the evidence supporting continental drift began to accumulate beyond any reasonable doubt. It took time, but eventually, the world would come to accept Wegener's bold and remarkably accurate prediction about the restless nature of our planet. The mid-20th century dawned with a new sense of urgency in the scientific community. While Alfred Wegener's ideas about continental drift remained intriguing, the lack of a concrete mechanism to explain it continued to frustrate geologists. Then, in the mid-1950s, a brilliant team of researchers led by Harry Hess at the Woods Hole Oceanographic Institution began to unravel a remarkable mystery hidden beneath the world's oceans. Hess and his colleagues were studying the patterns of deep-sea trenches and mid-ocean ridges, the long, underwater mountain ranges that run like wrinkles across the seafloor. They noticed something particularly peculiar. The ridges seemed to be constantly growing. It was a young geophysicist named Robert Dietz who made the truly groundbreaking observation. While studying the gravity measurements across the Atlantic Ocean, Dietz noticed a repeating pattern. The gravity readings were slightly higher in the mid-ocean ridges and lower in the surrounding areas. He realized this wasn't just a random fluctuation. It suggested that the seafloor itself was actually moving. This was a crucial step, a new way to think about the Earth's dynamic processes. Further investigation, aided by sophisticated new technologies like echo-sounding sonar and magnetometer measurements, revealed an even more astonishing discovery. Sonar allowed scientists to map the ocean floor in incredible detail, and they found that the ocean crust was relatively thin, only about 5–10 kilometers thick. What's more, they discovered that the seafloor wasn't a single, solid piece. It was made up of distinct plates, much like the Earth's continents. But the most compelling evidence came from the measurements of the Earth's magnetic field. Scientists realized that rocks contain tiny magnetic minerals, and these minerals align themselves with the Earth's magnetic field when the rocks cool and solidify. This creates a record of the Earth's magnetic field at the time the rock was formed. Hess and his team started to map the magnetic orientation of rocks on the ocean floor. They found that the magnetic poles, the points where the Earth's magnetic field lines intersect the surface, weren't fixed. Instead, they appeared to wander over time. More importantly, they discovered a repeating pattern, symmetrical bands of magnetic rocks running parallel to the mid-ocean ridges. These bands indicated that the Earth's magnetic field had reversed its polarity from north to south and back again many times throughout geological history. The remarkable thing was that the pattern of these magnetic reversals was mirrored on both sides of the mid-ocean ridges. The older rocks, furthest from the ridge, showed more complete records of magnetic reversals, while the younger rocks closer to the ridge exhibited only the most recent reversals. This demonstrated that new crust was being created at the ridges and pushed away from them, carrying the record of the Earth's magnetic field with it. This discovery provided the missing piece of the puzzle. It explained how new ocean crust could be created and how the continents could move, not through continents plowing through the ocean floor, but through the gradual spreading of the seafloor itself. The magnetic strip pattern, in conjunction with the discovery of seafloor spreading, provided the first undeniable evidence for plate tectonics, a revolutionary theory that would forever change our understanding of Earth's dynamic processes. The Earth isn't a solid, unmoving sphere. It's a giant puzzle, constantly shifting and reshaping itself, and the key to understanding this movement lies in what we call plate tectonics. Most of the Earth's surface is broken up into large, irregularly shaped pieces called tectonic plates. These plates aren't just floating on a liquid layer, they are embedded within the semi-molten mantle, a layer that behaves somewhat like a very thick, slow-moving syrup. The interaction between these plates creates a surprising number of geological features, and some of the most dramatic examples are found along divergent plate boundaries. Divergent boundaries are locations where tectonic plates are moving apart from each other. This separation isn't a sudden ripping. It's a slow, gradual process driven by the heat within the Earth. As the plates drift away, the pressure beneath them decreases, and the mantle rock starts to rise and spread out, much like a pot of honey cooling and widening. One of the most spectacular results of this spreading is the formation of mid-ocean ridges. These ridges are underwater mountain ranges that stretch for thousands of kilometers. The Mid-Atlantic Ridge, for example, runs right down the center of the Atlantic Ocean. It's the longest mountain range on Earth, and much of it lies beneath the waves. The ridge is actually a series of interconnected valleys and hills, constantly being built up as new oceanic crust is formed. As magma rises from the mantle to fill the space left by the separating plates, it cools and solidifies, creating new basalt rock, the dark, dense material that makes up most of the ocean floor. This process, called seafloor spreading, means that the mid-ocean ridges are continually growing outwards, pushing the older, denser oceanic crust away from the ridge. The youngest rocks are always found closest to the ridge, while the oldest rocks are further away, marking the path of the spreading plates. But divergent boundaries aren't just about mid-ocean ridges. They also create features on land. When continental plates pull apart, a similar process occurs, forming rift valleys. The East African Rift Valley, for instance, is a prime example. This enormous valley stretches thousands of kilometers through eastern Africa. Here, the African plate is slowly splitting apart, and as it does, magma rises to fill the gap, creating volcanic activity and shaping the landscape. The valley itself is formed by the repeated uplift and subsidence of the land as the plates separate. Over millions of years, this process creates a dramatic and diverse terrain. The heat and pressure from the spreading plates continue to sculpt the Earth's surface, reminding us that our planet is a dynamic and ever-changing place. The Earth's crust isn't one solid, unbroken shell. Instead, it's like a giant jigsaw puzzle, broken into enormous pieces called tectonic plates. These plates are constantly moving, though very, very slowly, just a few centimeters per year, about as fast as your fingernails grow. This movement isn't random. It's driven by heat deep within the Earth, and it's most dramatic at the boundaries where plates meet. Today, we're going to explore what happens when these plates collide, specifically focusing on a particularly fascinating type of collision known as a subduction zone. Subduction zones are found where one plate slides beneath another. It's a powerful, grinding encounter, and the forces involved are immense. Typically, a denser plate, one with more mass, will sink beneath a less dense plate. The Pacific Ocean is home to a vast network of these subduction zones, and they are responsible for some of the most dramatic geological activity on our planet. Let's consider the scenario of an oceanic plate colliding with a continental plate. The denser oceanic plate is almost always the one that subducts. As it descends into the Earth's mantle, it heats up dramatically. This heat, combined with the immense pressure, causes the rock to melt. Think of it like putting a piece of ice in a hot drink, it melts. This molten rock, or magma, is less dense than the surrounding solid rock, so it begins to rise. This rising magma doesn't just disappear, it forces its way upwards, eventually erupting onto the surface. These eruptions aren't like gentle bubbling, they can be explosive and violent. Over time, repeated eruptions build up a chain of volcanoes along the edge of the subducting plate. A classic example of this process is the Andes Mountains along the western coast of South America. The Nazca Plate, a dense oceanic plate, is subducting beneath the South American Plate, a lighter continental plate. This ongoing collision creates the towering Andes and generates a long, linear chain of volcanoes. However, the story doesn't always end with volcanoes on land. Sometimes, the subducting plate doesn't slide directly beneath a continental plate. Instead, it might descend beneath another oceanic plate. In this case, the magma doesn't directly create a volcanic arc on land. Instead, it rises to the surface, forming a chain of volcanic islands. The most famous example of this is the Mariana Trench and the Mariana Islands. The Pacific Plate is subducting beneath the Philippine Plate. The magma generated by this process doesn't create a volcanic arc on the Philippine mainland. Instead, it rises to form the volcanic islands of the Mariana Islands, and the deep, dark Mariana Trench, the deepest point on Earth, lies directly above the zone where the Pacific Plate is subducting. The interaction creates intense geological pressures, leading to frequent earthquakes, further emphasizing the dynamic nature of these plate boundaries. These zones are fundamentally shaped by the constant, relentless push and pull of the Earth's moving plates. The Earth isn't a solid, unchanging sphere. It's a giant puzzle, constantly being reshaped by powerful forces deep beneath our feet. We've already seen how pieces of the crust, called tectonic plates, move across the surface, driven by heat and convection currents within the Earth. These movements create dramatic landscapes, from towering mid-ocean ridges to the deep trenches where old oceanic crust disappears. But the most visually striking and potentially dangerous interactions happen at something called transform boundaries. At a transform boundary, two tectonic plates are sliding past each other horizontally. They're not colliding, nor are they moving apart. Instead, they're locked together, attempting to continue moving but stubbornly resisting. This creates immense stress, building up like tension in a tightly wound rope. The plates aren't going to simply slide smoothly. That would require enormous amounts of energy, and the Earth doesn't work that way. Instead, the stress builds until it overcomes the friction holding the plates together. Suddenly, with a jarring release, the plates slip past each other. This isn't a gradual movement. It's a rapid, jerky displacement, and that's what generates earthquakes. These sudden movements are concentrated along what we call fault zones, breaks or fractures in the Earth's crust where the plates are grinding against each other. Fault zones are often characterized by visible features, like steep cliffs or scarps, marking the abrupt change in elevation that results from the movement. The San Andreas Fault in California is a famous example. It's a transform boundary where the Pacific Plate is sliding past the North American Plate. The immense pressure and strain along this fault zone are responsible for the frequent earthquakes that shake the region. It's important to understand that not all earthquakes originate from transform boundaries. However, a significant proportion do. The intensity of an earthquake, how strongly it shakes the ground, is directly related to the length of the fault zone and the amount of stress that has built up. Longer, more stressed fault zones tend to produce more powerful earthquakes. Scientists use sophisticated instruments called seismographs to detect and measure these earthquakes. These instruments record the ground shaking, allowing them to pinpoint the location of the earthquake and determine its magnitude, often measured on the Richter scale, a logarithmic scale that reflects the amplitude of the seismic waves. The patterns of seismic waves radiating from an earthquake's epicenter, the point on the Earth's surface directly above the earthquake's focus, the actual point of rupture within the Earth, provide valuable information about the depth and geometry of the fault zone. Furthermore, scientists study the rocks surrounding fault zones, analyzing their structure and composition to gain a better understanding of the forces at play, and to predict, as accurately as possible, the likelihood of future earthquakes. The study of transform boundaries and fault zones is a constant process of learning and refinement as we continue to unravel the complex mechanics of our dynamic planet. Deep within the Earth, far below the crust where we walk and build, a very special kind of heat is constantly churning. It's not heat created by friction at plate boundaries, though. This heat originates from the very core of our planet, from the process of radioactive decay in the Earth's mantle. This heat isn't just randomly distributed. It tends to rise, just like warm air rises from a hot stove. This rising heat, concentrated in certain areas, creates what scientists call a mantle plume. A mantle plume is essentially a column of hot, buoyant rock that slowly ascends through the mantle. It's like a giant, slow-moving conveyor belt carrying molten material upwards. The exact shape and size of these plumes are still being researched, and their influence is a topic of ongoing scientific debate, but we know they exist and play a vital role in shaping our planet's surface. One of the most compelling examples of a mantle plume in action is found in the middle of the Pacific Ocean, the Hawaiian Islands. These islands, stretching across hundreds of miles, aren't formed by the powerful forces of plate boundaries like those we've discussed. Instead, they arose from this quiet, persistent upward movement of heat. The theory suggests that long ago, a particularly strong mantle plume began to rise from deep within the Earth, perhaps around 70 million years ago. This plume carried molten rock, magma, towards the surface. As the magma approached the crust, it erupted, forming a chain of volcanoes. Because the Pacific Plate is moving slowly, very slowly, across the top of this rising plume, the volcanoes remain stationary relative to the plate. This is crucial to understanding how the islands formed. Imagine a boat sailing across a calm lake. The boat doesn't move across the water, but the water flows underneath it. The Hawaiian Islands are like that boat, drifting slowly over a stationary volcanic hotspot. As the Pacific Plate continues its journey, the volcanoes created by the hotspot are progressively carried away from it. The older, inactive volcanoes form the northwestern islands, while the islands to the southeast remain active, constantly building upwards as new lava erupts from the plume. This creates a chain of islands, a volcanic island arc, with the youngest, most active volcanoes located directly above the hotspot. Scientists track the age of the Hawaiian Islands by dating the rocks formed by volcanic eruptions. The youngest rocks are found on the Big Island of Hawaii, while the older, eroded islands to the northwest provide a record of the hotspot's movement over millions of years. This ongoing process continues today, evidenced by the continuous volcanic activity on Kilauea and Mauna Loa. The Hawaiian Islands are therefore a stunning demonstration of the power of a mantle plume, a quiet, persistent force that can sculpt entire landscapes over immense timescales. It's a remarkable story of Earth's internal heat and its remarkable ability to shape our planet's surface. The Earth isn't a static place, not really. It's constantly moving, though most of the time we don't feel it. But there's a secret way we can actually see this movement, a subtle magnetism locked within the very rocks themselves. This is where paleomagnetism comes in. It's a detective's tool for uncovering the Earth's ancient history. Essentially, rocks, when they form and cool, can remember the direction and intensity of the Earth's magnetic field at the time. It's like a tiny, internal compass that's been preserved for millions of years. The Earth's magnetic field is generated deep within its core by the swirling movement of liquid iron. This creates a magnetic north and a magnetic south, just like a giant bar magnet. Now, as rock cools, magnetic minerals within it, primarily magnetite and pyrrhotite, align themselves with this field. Once the rock solidifies, this alignment becomes fixed, creating a record of the magnetic field's orientation at the time of formation. Scientists study these rocks, especially volcanic rocks, which are formed rapidly and therefore often have very well-preserved magnetic signatures. They measure the strength and direction of the magnetism. The crucial part is that this magnetic orientation isn't constant. The magnetic poles wander over time, sometimes dramatically. This wandering is linked to the complex dynamics of the Earth's liquid core, where the flow of molten iron constantly shifts the direction of the magnetic field. Now, here's the truly remarkable part. Different continents have recorded the magnetic field at different times and in different directions. For a long time, it appeared that the magnetic poles were always in the same location relative to the continents. But as scientists collected more data from rocks across the globe, they began to notice a pattern. The magnetic signatures of rocks on what we now know were South America and Africa were pointing in different directions. This indicated that the continents themselves had moved over immense periods of time. It was as if the continents were slowly drifting across the planet, and the rocks were recording that movement. The key was realizing that the apparent wandering of the magnetic poles wasn't a global phenomenon. It was relative to each continent. The direction of magnetism wasn't fixed to a single point on Earth, but rather to the continent itself. By carefully analyzing the magnetic data from rocks on different continents, scientists were able to create reconstructions of what the world looked like millions of years ago. It was like piecing together a giant puzzle, with the magnetic signatures of rocks acting as vital clues. This paleomagnetic data, combined with other evidence like seafloor spreading and fossil distribution, ultimately led to the revolutionary theory of plate tectonics, the understanding that the continents aren't fixed in place, but are constantly moving, carried along by the slow, grinding movement of the Earth's lithospheric plates. It's a beautiful example of how seemingly subtle clues can reveal the grandest stories of our planet's past. The Earth isn't a solid, unchanging sphere. Beneath our feet and stretching deep into its core, it's a restless giant, constantly shifting and reforming. This movement, driven by immense forces within the planet, is fundamentally linked to the locations where earthquakes and volcanoes are most frequently observed across the globe. The way plates interact, not just at boundaries, but throughout the entire system, creates a dynamic, often violent process. The deep Earth isn't uniformly hot. There are zones of increased heat concentrated beneath the plates, areas of intense melting. As the mantle flows, this molten rock magma rises towards the surface. Where this magma encounters weaknesses in the overlying crust, it can erupt, forming volcanoes. However, the location of these volcanoes isn't random. They are invariably situated along plate boundaries, particularly at subduction zones. At subduction zones, one plate, typically a denser oceanic plate, is forced beneath another, often a less dense continental plate. As the oceanic plate descends into the mantle, it heats up and partially melts. This molten material then rises through the overriding plate, creating volcanic arcs, chains of volcanoes that run parallel to the trench formed where the plates meet. The Andes Mountains in South America and the Cascade Range in North America are excellent examples of such volcanic arcs. But the connection between plate movement and seismic activity isn't limited to subduction zones. The sheer strain and stress built up as plates grind against each other, even without direct contact, can trigger earthquakes. Large-scale plate collisions, like the one that formed the Himalayas, generate enormous forces that propagate through the crust, accumulating until they are released in the form of powerful earthquakes. Similarly, along transform faults, where plates slide horizontally past each other, the friction between the moving surfaces can build up tremendous pressure. Furthermore, the stresses created by the movement of plates aren't uniformly distributed. They tend to concentrate in zones of weakness, fractures, and faults within the crust. These weaknesses can act as pathways for magma to ascend, further contributing to volcanic activity. The frequent earthquakes surrounding the Pacific Ring of Fire, a zone encompassing many of the world's largest earthquakes and volcanoes, illustrate this beautifully. It's a region where the Pacific Plate is being pulled in multiple directions by surrounding plates, causing enormous deformation and stress. The patterns of earthquake and volcanic activity are therefore intrinsically linked to the mechanics of plate tectonics. They're not isolated events, but rather expressions of the Earth's ongoing, powerful, and often unpredictable dance. Scientists study these patterns, analyzing the location, magnitude, and frequency of earthquakes and volcanic eruptions to better understand the forces at play and, ultimately, to anticipate and mitigate their potential impact. The Earth is constantly reminding us that it's a dynamic system, perpetually reshaping itself, and we are fortunate to witness, however briefly, its immense power. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. The continents have shifted, moved, and reformed over eons, a silent ballet beneath our feet. Now, let your thoughts drift, calm and unhurried, like the slow currents of the Earth itself, until sleep finds you. Good night.